This video is going to provide a quick roll through of example number 10 from our chapter 10 example kit. And it's going to work with, again, the difference of two means and a hypothesis test. And this one's just got a little added wrinkle, which I thought was useful and deserving of a separate video. We're typically just been looking at an assumption with our hypothesis testing just on a baseline of, hey, the means are the same. Well, sometimes we might agree that the means are at least different. And so we'll take a look at that type of problem in example number 9. So if a company that makes hotel toilets claiming that a new toilet reduces the average amount of water used by half a gallon per flush compared to the current model. What did they do? Well, they ran SRS, 30 toilets of each style, and in those 30s they measured the sample mean in terms of the amount of water that was flushed and the standard deviation associated with those, in this case 30 different toilets, 30 flushes for that matter as well. And so we're going to run a significance test. By the way, we'll run it at alpha equals 5%, as we've done so many more times, to see, does this new pressure-assisted toilet really meet the claim that it uses half a gallon less per flush than the current model toilet? So let's talk through a couple things. I'll start on the right. Are all our conditions at least met that we can run this two-sample t-test? And we'll find out that the answer is yes. Number one, we had an SRS for each of the current and new model toilets. We can assume also that there are at least 300 toilets of both model types that could have been picked from. And lastly, we had a sample size in both cases, N1 and N2 of both 30, which allows our central limit theorem to apply. We therefore have all the conditions to go ahead and do a two-sample t-test. And again, as previously said, we'll run it at a 0.05 significance level. So in red, I've accumulated all our stats again, C for current and for the new model. And what will we work with? Well, let's say, hey, more than, what's that at least mean if that's what they're claiming? Well, we'll have to assume that the more than amount that they're looking for, we can work with, will kind of give them the belief that this new model is more efficient. So what's that saying? Well, our hypothesis is the average amount used by the current model minus the average amount used by the new model, we'll say is equal to 0.5. Sorry if that looks like it's a not equal to sign. Let me just clear that just for absolute perfect clarity. We're going to say, all right, well, that's kind of what the status quo. What's our null hypothesis? Well, it's what's stated in the problem, that if we take the amount of water used by the current minus the amount of water used by the new, we're expecting that it's going to be greater than 0.5. That's how much water we'll be saving, at least 0.5 gallons per flush with this new model. So what's the deal? Just as before, we're going to compute a t-statistic with the one new little wrinkle that value right here, the mean of the current minus the mean of the new, in our null hypothesis, we're usually saying UC minus UN equals 0. Well, we got something slightly different here. What does that mean? Well, instead of just this becoming a blanket minus 0, this value here in the parentheses, it's now going to take on a value of 0.5, because that's what our null hypothesis says. So we do have a little bit of freedom here. You don't have to necessarily think your null hypothesis, you're always setting things equal to each other. Typically you might be, but if not, it's a very simple adjustment and we're fine here. Some of you might thought, well, maybe I could just tweak one of these two parameters, either reduce the current by 0.5 or increase the new by 0.5. Either way, that would be fine to get us to the same place. But the bottom line, leave your variables alone. Just let this part, what your null hypothesis is stating, be the difference. It'll handle it fine, just like that. You can see I got my standard error again, 0.29 squared over 30, plus what? 0.18 squared over 30, all the square root of that. And what will I wind up with? Well, 1.64 minus 1.09, 0.55. We already talked about this part being the 0.5. My numerator becomes 0.05. And when I do all my work with the variances being added, add them together, take the square root of said variances of the sample means, what will I wind up with down here? A value of 0.0623. Run those numbers, numerator divided by denominator. I'll come up with a t-value of 0.8024 after some rounding. All right, t-value. Now throw it into your probability model. Did a little bit of calculator work here. This is kind of minimal calculator approach. Again, remember, I'm not using the whole lovely t-test that our calculator would do. I'm going to work with our conservative degrees of freedom of what? In this case, I got n1, n2, both 30. Degrees of freedom will be 30 minus 1, 29. And I'm looking for values greater than 0.8024. I'll run that through my TCDF. I'll come up with a probability. Excuse me, thought I was going to sneeze in the middle of the video, but I guess I didn't. I'll come up with a probability value just slightly greater than 21.4%. Since that value is well larger, much larger than our alpha level, the 5% significance level, I'm going to fail to reject the null hypothesis. I don't have convincing evidence to suggest that this toilet, this new model, is actually saving that much of flushing per gallon. I'm just going to have to go ahead and live with this. I just can't believe that it can do more than what they're saying. They're claiming the alternative is what really exists. What I found out through my hypothesis testing, I do not have sufficient evidence to suggest that it can do more than 0.5. I can be okay with that. I can be okay with not rejecting the null hypothesis. No problem there. I just can't get to the point where I think this thing saves me any more water. So that's kind of the bottom line as I work through this. Again, simplest way to handle this statement right here. You're going to fail to reject the null hypothesis or believe that the savings are nothing better than 0.5. We have nothing to indicate, don't have convincing evidence to suggest that the claim that it saves more than half a gallon per flush is out there. So this is example 9. Hope it helps you out just a little bit. It's a slightly different way of looking at some problems, which is why I wanted to spend some time with it, and continued good luck as you work through this section.